Carl is, in addition to being CEO and technologist, also a maker. So let me start with the maker-in-chief.
Okay. Is there a clicker? Good morning, everybody. So, at least we get the sound loud now. So I've been making things for, I don't know, 40 years or so, something like that. You know, I've actually gotten to the age where it's really pleasing to still be the youngest one and the least experienced of making things of our whole panel. So even though I've been making things for 40 years, I'm kind of the junior achiever when it comes to this celebrated little group. So the two things I've been doing is I've been involved in the design and making of software, and software particularly for design and fabrication of things. So I've been involved in CAD and CAM on the professional side, and as well, I've been making things for about 40 years or so. I built about, I was trying to count this morning. That's the other problem when you built enough things. It's 9 or 10 boats that I built. Something as small as this, the largest one was a 38-foot sailboat, so a whole range of different craft. Also built a number of houses. And then over the last couple of years, I'm just kind of giving a tour through a bunch of things I've been doing. This is a bowl that I did. What was interesting about it is it's one of the design experiments I felt like I was doing more recently that was smaller and more tangible. I tried a dozen different ways to make this thing, and the only one that worked in the end was to 3D print it. And so particularly the one that's in the upper left is a mix of stainless steel and fused with bronze that was 3D printed. And it was really interesting to go through all the traditional techniques. I do remember bringing it over to Bruce's and showing it to him and saying, how do you think I made this? And he was like, you know, and the way that us makers kind of interact with each other, you turn it upside down and you want to scratch it. And if I had let him, he probably would have cut it in half to try to figure out exactly how he made it. And he even took it to a bunch of his friends and none of them could actually figure out. And at that point, I realized that we were really onto something with 3D printing, where it was getting to the place where you could start making real objects. I'll have a little bit more to say about that. This is also an interesting, I did a series of these vases. This is cast in bronze. The original ones I did where the original piece was made out of wood and then it was used as a mold and it was cast. And then I went to making one. The next one has a twisted design. The ribs on it kind of spiral around it. And in that one, what was interesting about it was that I used a 3D print as the mold for casting. So my plastic became the lost wax. Unfortunately, it was environmentally idiotic. I used ABS. My friend who runs the foundry was kind enough to do it just once and told me enough of this. And Bruce is going to talk more about having, we've collaborated on this for a number of years, and Bruce has taken it to an entirely different level. And I'm really excited about turning it into something that's really useful and environmentally friendly again. And then this is another set of things I made. This is a bench that's carved out of granite. There's actually 3 versions of this. One is made out of wood, one was CNC'd out of foam and cast in bronze, and this one was out of black granite. Oh, and this is the last project, the most recent. This is actually just a rendering, but it looks almost identical. This is an electric go-kart I built with my son. And what's interesting about this range of work, all of the early work, including the boats, were all done in analog fashion. There's not a digital thing involved. There's no digital tools in the design, and there's certainly no digital tools in the fabrication. All the later ones go through this period of exploration of starting to use digital tools, and then things like the go-kart are just this weird mix of analog and digital, which I think really is the future, where there is no real distinction, and a digital tool is just a tool. So this was entirely designed on the computer, but it was also prototyped in the real, and it was simulated as well and visualized, but it was done with very traditional analog techniques. And I think we're getting to the point where we're starting to be able to move designs from one side of the screen to the other. And it had always frustrated me tremendously that we worked so hard to get to the design on this side to look perfect, but we kind of abandoned everyone in taking the thing on this side and turning it into a physical artifact. And I think a lot about the conference today is really about making that membrane permeable. So you can move things from here to the other side into the computer so you can compute on it. Once you can compute on it, you want to fabricate it again and move it back. And a lot of what we're all going to talk about is that movement of ideas, you know, from your mind into the physical world and back again. So when I'm not being CEO, you can find me in one of my shops. This is my shop. This is the metal shop. I'm busy building shop furniture, which is just taking old machine castings and combining it with new stuff. There's nothing like building furniture with 1.5-inch Acme threads. I have not found a piece of furniture that would not benefit from an 1.5-inch Acme thread. And this is me in my wood shop along with my woodworking robot, who now, unfortunately, I thought it was going to save me tremendous amounts of time. There's two funny parts of it that are somewhat ironic. One is when you have one of these big machines that you think is going to save you all this time, the first thing you do is you stand in front of it all day long just watching it do work. So you go from actually doing work to just standing there, and then when it's actually done, you have a ton of stuff left to sand. So I thought it would save me work. It has created way more work for me than I ever imagined. So let me move on to really what the theme of the conference is, you know, with this background that you have of what I like to make, which is all about capturing, computing, and creating. And let me show you some of the capture stuff. And there's so many people today who have already done a great job, and there's many more over the next day and a half who are described this act of capture. But I chose 3 different examples that come from our customers and partners of doing interesting and representative work in terms of capture. So here's the first one. So this is a capture of Market Street in San Francisco. I mean, just, you know, from where we've come from, where we used to, you know, get thousands of points, tens of thousands of points, to be able to capture this, there's not a photograph in there, that is entirely a point cloud that's captured. And we're going to hear a little bit more around this project today. But I think it's kind of amazing. And in some ways, it starts speaking to this thing of we're going to be able to capture tremendous amounts of data. The real question is, what are we going to be able to do with all of this data? Here's a second one that I think is really exciting. So this is an Avatar. So this is Jim Cameron making Avatar. What people may not realize about this is every bit of motion for the movie was captured. So this is the first feature-length movie in which every bit of motion for it was captured. And so it has this really different dynamic than what usually goes on in capture. Most of us are spending all of the time trying to capture the geometry and the topology of what we have. This one instead says, I already have the geometry and the topology. It's the 11-foot blue people. What I need to do is get realistic motion. And so what they were able to do was capture everything, whether it was a horse, whether it was a person, or in many cases, really low tech, like the flying spaceships. They actually made out of wireframes of hangars. And they just moved them around and took the motion of that and turned that into the movie. So a really interesting high-tech, low-tech combination. Is this just me? Okay, we'll ignore that. Here's another example that you can see a lot of. This is a factory. So 3 different settings, one in terms of media and entertainment, one in terms of a factory, the other is the built environment. All really interesting places where there's a lot of data being captured. And we do have to figure out how to compute it. And if you look at the Avatar one, that was the one that was most ready to plug and play in terms of they were able to turn it into a computable model. And I think that's really the important thing, is how do you take this data and be able to compute on it? Just visualizing it is interesting. It's not enough. The other thing about it that I think is particularly interesting, it starts leading to this idea of different kinds of representations of the information inside the computer. So In many cases, we've historically worked with analytical surfaces. But as we start gathering point clouds, it's going to become more realistic. And discrete forms of data in terms of point clouds or meshes are going to become more reasonable. And in the end, we will be able to do many of the things that people think are unimaginable, like drive CNC tools, even off data like this that's actually discretized as opposed to continuous data. Okay, so let's just look at the compute. So here's an example. This is a classic, I think Stuart talked about this morning. Many people have fancy names for it. I still see it as reverse engineering. You have a part that already exists in the world. This is a new product that we just brought out called Fusion, cloud-based CAD system. What was important about it is that you can start taking in data that already exists in the world. And you can bring in this data and you can transform it through different data representations. So while people talked about, and Stuart did as well this morning, about these workflows, I actually think the thing that's getting in the way of these tools being really useful is that the workflows are really very much too painful. So while the point tools are good in and of themselves, the place where the fidelity, the place where the pain enters the process is moving from one to the other. As he said, I moved it 11 times in an hour. My head hurts from the idea of moving between tools 11 times in an hour. And so we worked hard on trying to build a tool that said, this is built around the idea of I'm going to work together with other people. So two important considerations. One, I'm going to work with other people and we're going to collaborate and I'm going to know what's going on. And the second thing is I can go all the way from ideation to fabrication in the tool. And we also here we show it runs on all kinds of Macs and PCs and things like that. But that you can end up in the end taking this, like something that comes in as a point cloud, and eventually be able to fabricate it in a CAM tool. And so we're really interested in trying to avoid these places where the data just kind of falls into a dark hole. And what bothers me most about it is the difficulty in going back and forth. And that idea of iteration seems so important to me in the way that you make things, that you need to do iteration all the time. And when the tools prevent it, I think it prevents you from making the best things possible. Let me move on to one other thing that has me particularly interested, and this is this idea of generative design. And it's different than what we see going on in the world where we're going to capture something. This is a different idea in which it starts with the idea that computing is virtually free and it's virtually infinite. And if you had all the computing in the world, how would you design and engineer things differently? And that's what was the starting point for what we were thinking here. And at first we said, let's just test exhaustively. And that certainly yielded some results. But then we said, what we really want to be doing, because in the world of CAD, computer-aided design, I would say in the 30 years that CAD has existed, the computer has barely ever aided in the design of anything. It started, it's true. It started 30 years ago, and we did 2D documentation. We agreed upon a convention, and I made a blueprint, and I transferred it to you. Today, we do the same thing with 3D models. We document our ideas. We do not design in these tools. And the idea is we need to reach the place where these tools actually help us. So here's this idea of generative design. So imagine we have something, fills a space envelope. And there are two fluids in it, and they're going to pass by each other, and there's thermodynamic requirements about exchanging heat. And all we're going to talk is about a high-level specification of what we want. And now we're going to let the computer, and remember, we believe that computing is virtually free. So we're going to let it run for hours, thousands of hours, tens of thousands of hours. And there's the heat exchanger that the computer designed. So it's one of these interesting things. It makes a lot of designers, I'd say almost angry, that the idea that, but I look at it as it's just another one of the tools. It's another technique that we have that will start getting at it. What's interesting about this design and several others like it, it explores the space in a way that guarantees you a near optimal solution. And there are very few times. As a matter of fact, we did another one for a part of the motorcycle, an electric motorcycle. We were working on the swing arm, and we ran it through the same algorithm, and the result that comes out looks almost identical to a dog or a cat pelvis, except it has a hole on one side. And we say to ourselves, this has to be a bug in the algorithm. And it turns out, of course not. Unlike a dog or a cat, the loading on a swing arm on a motorcycle is asymmetrical because the chain is on one side. And so it was interesting because when I went back and you go to the Google and you look at the images, and what the Google tells you is that all the swing arms have ever been designed for motorcycles. Nobody ever picked up on this fact. So I think there are insights that we can learn and that we need to be a little less proud about letting computers start helping us design and engineer things better. Here's another example just like this. This is one, it's growing a structure, and this is for a hip cup. And the idea behind the hip cup was to make a structure in which the foam has pores that are pseudo-random in size. And the reason is that it's demonstrably better in terms of having the bone grow into that if it is pseudo-random as opposed to a regular structure. The body recognizes that as weak bone and grows into it much better than if it's a regular structure. So we worked with a customer on being able to do this. And really the interesting thing that comes up in stuff like this is because this one will be different for everyone who gets one, all of a sudden you have to get the FDA not to approve a device, but the FDA has to approve an algorithm. And if you think it's hard getting the FDA to approve devices, getting them to approve algorithms is really hard. Okay, so let's just move on to the next part, which is create. And one of the things we got interested in was 3D printing. And the genesis of it is really when you look at what we're doing with generative design. So if you think about it, why is Autodesk interested in 3D printing? It's only because those shapes that are coming out of generative design are really difficult to fabricate in any other way. And I think we're on the verge of getting to the place where we will start being able to truly use additive manufacturing to be manufacturing, to make real products that go into the world. This was our first attempt at a printer. This is just released. It's called the Ember. It's a relatively small scale but high resolution printer that we're selling. The important thing about Ember was that it has 3 ideas built into it. One is an open software platform called Spark that we want others in the industry to use, and we're working with others to adopt. It's an open hardware in which we're publishing the design, and people can take the design and riff on it, and they can take the design and build others or improve upon it, and we're hoping they do. And the third one, unlike other 3D printer manufacturers, we are encouraging people to experiment with materials. We want people to put their own materials in so that we go forward in material science. So open hardware, open software, and open materials. Let me skip that and move on to some other things in 3D printing. 2 things that I'm particularly interested in 3D printing these days. We're seeing a new generation of machines. This is called the Mark Forge, but there's a whole series of them in which they are now taking plastic parts and putting in filament. So you have fiber reinforced plastics. This one does Kevlar and carbon fiber. And all of a sudden you're starting to turn those unusable plastic parts into truly manufactured goods. So that one's interesting. Second one, there's another company I visited again yesterday. They are now printing plastic parts at about 100 to 150 times the speed of the standard SLA or FDM printers. So for the first time, you can actually see the print taking place before your eyes. So things that took 12 hours are taking 6 minutes. It's incredible when you're able to do that. So I think we really are on the verge of really important stuff where these things will no longer be prototypes, but they will be used in real production. Let me show you some other stuff I'm interested in digital fabrication. This is some work going on at the University of Stuttgart. This is Akamenga's work, in which he's using 2 highly coordinated industrial robots to do wet layup of things like carbon fiber. I just love the choreography of this. We'll just watch it for a second. And there's the architectural size structure that's digitally fabricated. So I think this is amazing. We're now getting to the place where we can start designing truly interesting things in the computer with its help and being able to fabricate them. Here's another technique I'm equally interested in. Again, for me, most of these things are not about being dogmatic. It's purely practical. I think there are huge advantages to additive manufacturing that I talked about, such as shape complexity being free, the efficiency of materials, but there's also the precision that you get and surface finish that you get things from subtractive. And so what I like about this is the combination of additive and subtractive, where you really get the benefits of both. So, how does this all come together? That's what we're here to talk about. It's the capture, compute, create. For me, the capture is the first part. It's really important, but if we can't get it into a computable form, it makes little sense. And I spent a lot of years in which we kind of abandoned people at that side of the screen with a computable model. What I'm most excited about is bringing it to the other side and being able to now fabricate these things. So just like Ethor said and the folks from Unique, here's an example of a story. We bring in scan data for a prosthetic device. This was done by our friends at Amped, a woman who had lost her leg in Afghanistan. That's the scan of it. She was an avid sports photographer, nature photographer, and wanted to get back to being able to do that. And this is stuff where it's brought into Fusion, turned into an analytical surface. Here you can see the shield being actually built. And it'll go all the way through fabrication. Here's a little bit of analysis on it. So we can actually start to build digital prototypes, really understanding how this thing's going to perform. So I'll move it along a little bit here, but you get the point. And there's the finished product. So this is all being done in the cloud. This is a product that sells for $25 a month. And by the way, students, faculty, institutions around the world, it's free. Anyone who does this for hobby or nonprofit, it's also free. So for $25 a month, we're starting to get things where we can scan data in the world, bring it in, model it, compute upon it, analyze it, and fabricate it all in one place, and visualize it just like that. So I think that this is, kind of the future of how we're going to make things. And it always strikes me as odd as people are doing this amazing building of these things for the future that they're using 20-year-old tools to do it. And so I feel that our obligation at Autodesk as tool makers is to bring the latest, greatest tools and do our small part in bringing the industry forward by really making these tools available to everybody. And here it is, available on a mobile device. And there she is, being able to go off-road once again and be able to do nature photography. Thanks very much.